Okay, so good morning. We are the Mars and Lunar Lander Engineering Team, also known as MALLET. Our members are Sam Bayer, Alexander Benvenuti, Jared Chown, Christian King, Angela Lalovic, Matthew Snyder, Justin Rauchworth, Rodolfo Rodriguez, Daniel Rossman, and Sierra Vidalis.
So I'll start by going over our mission overview and our concept of operations. Thank you. So yeah, I'll start by going over our mission overview and concept of operations. So the EEV will be prepared on Earth with all of the appropriate software and stuff loaded on. It will depart to the Mars parking orbit on November 19th, 2036. We expect that trip to last about 800 days. And then it will wait around until January 1st, 2040, when we expect the Mars Deep Space Transit Vehicle to arrive. And then a few days later, so that the orbits line up, we will depart from the DST to Deimos on January 3rd and arrive 1 day later on January 4th. We'll spend 9 days here collecting samples that'll be stored on the rover. And then after those 9 days, we'll depart from Deimos to Phobos, where we'll spend, and that travel will take 1 day. And we'll spend 13 days on Phobos collecting samples that'll again be stored on the rover before we then depart back to the DST, arriving January 28th, when the mission will be complete. Next slide.
Okay, and so for the trajectory design, as you can see, on January 3rd, the EEV will begin its 1-day transfer to Deimos. Time of transfer is 1 day. It'll arrive on January 4th at noon, and the specific impulse required for that is 0.688 kilometers per second. Next slide. After the EEV is done gathering samples, it will then begin its 1-day transfer to Phobos from Deimos. It will arrive on January 14th after departing on January 13th, and the specific impulse required is 2.27 kilometers per second. Next slide. After the EEV collects samples from Phobos, it will then have to rendezvous with the DST in the parking orbit. It will also be on a 1-day transfer starting on January 27th. It'll take 1 day to get there. It'll arrive on January 28th, and the specific impulse required for all of that is 1.26 kilometers per second. Next slide.
Yeah, so beyond determining what time to leave Earth, the only other way that we could really optimize the orbit was to evaluate which sequence we were going to visit the different moons at. And so we conducted a trade study to try to figure that out. And so on the left column, you could see the characteristics of going from Deimos to Phobos to the DST. And the right column has set the characteristics of going from Phobos to Deimos to the DST. And so the two principal design considerations that we evaluated were the total delta V required and the mission time. And so we came to the conclusion that although the mission time from Deimos to Phobos is slightly longer than the other way around, the con is greatly outweighed by the less delta V, and then that's represented in the final score. And that's ultimately why we chose that orbit design. Next.
So I'll start off our discussion of our systems with the docking system. So to meet our objectives, the docking system has to have certain requirements. It's first going to have to dock, the DST is going to have to dock with the EEV upon the initial rendezvous. Then the EEV will need to dock with the DST upon the departure rendezvous. And this whole docking process should be automated. Our design will use the International Docking System Standard because it's currently used by NASA and it's likely to be what's used for the DST. The complete guidelines can be found in the interface definition document, and the design will need to feature active docking, so it can dock with both the EEV on the way in and the DST on the way out. Next slide.
So the EEV is split into the lander and service module. And so the lander will be, the entry, descent, landing ascent system will be on the lander. So the total minimum delta V is 0.024 kilometers a second. We rounded up to 0.05 kilometers a second to add for margins with propellant in the design. Next slide, please.
So due to the lack of a substantial atmosphere on both moons, aerobraking and parachutes are not a viable option. Therefore, we must use a powered descent sequence to land on the surface of each moon. The lander will feature autonomous landing capabilities via NASA JPL's technology that was developed and used in the Mars 2020 mission. One of the key features of that descent system is the use of terrain relative navigation, which can reduce the spacecraft's relative position error down to approximately 40 meters as opposed to Earth-based navigation, where the position error is on the order of several kilometers. Upon descent, images from the lander are captured and compared to an orbital map that has been preloaded onto the lander's computers. By processing the surface images and identifying landmarks, the spacecraft can estimate its position in space to a higher degree of accuracy. Using this position, the guidance, navigation, and control system selects a landing point that is viable given the amount of fuel on board, and that also avoids any potential hazards. Next slide, please.
We chose a pure oxygen environment at 0.3 ATM to combine the weight savings of having a one gas system and the low fire risk of a lower pressure cabin. To sequester the CO2, this mission will utilize lithium hydroxide canisters because they are both lighter and cheaper than a CDRA. Rather than using a complex and slow space garden, astronauts will eat MREs, which are lightweight and full of nutrition. Next slide. We will use a radiation shelter to keep the astronauts safe. It will consist of a bag that fits along the sunlit side of the spacecraft and will be filled with water in case of a solar flare. This mission will also use water recovery system to save on the water brought along. The exercise system will consist of an elastic band that the crew will use to keep in shape. Finally, to manage the waste, this mission will utilize waste bags because they're lightweight and cheaper than a space toilet. Next slide.
We will be utilizing a rover to achieve our scientific objectives and sample collection requirements of the mission. The image on the right depicts a CAD rendering of our Mallet rover with a few features denoted. Inspiration for our design was taken from proposed rovers that have a similar objective in missions, such as NASA's Viper lunar rover and JAXA's MMX Martian moon rover. The rover will be loaded and stored in the lower module of the EEV lander/service module. Overall, the largest limiting design factor is size and mass due to the fact that the rover and any samples collected must be taken to and from each moon with the EEV. The overall size of the rover is approximately 1.4 by 1.5 by 1.6 meters and will have a mass of approximately 250 kilograms. The rover will communicate with the EEV directly, but will utilize the Mars Relay Network of orbiters around Mars to communicate with the Earth, which is similar to how the EEV will communicate and will be further discussed in the telecommunication section of the presentation. The three types of antennas that will be used on the rover include ultra high frequency and X-band low gain and X-band high gain. And they are indicated on the image of the rover to the right. The ultra high frequency antenna will be used as the primary method of communication, while the X-band antennas will be the secondary method. A total of 50 kilograms of samples will be collected on each moon using the rover and will be stored in the EEV until it finally returns to the DST. The low gravity wheels included in the design are inspired by the JAXA MMX rover and are specifically designed for increased traction in the low gravity environment of Phobos. The wheels each include 10 grousers, each with a teeth-like pattern. And moving on to the next slide.
So there are three scientific objectives that we want to achieve when studying Phobos and Deimos. The first is gaining an understanding of the elemental and mineral compositions, both on the surface and below the surface. And this can be achieved by utilizing scientific equipment, which I will mention, and also by collecting samples and bringing them back to Earth for further analysis. So on top of just getting an understanding of the composition below the surface, we're also interested in seeing if there's any signs of water ice below the surface, which many studies have suggested it exists. And finally, based on these two objectives, you should also be able to get a better understanding of how these moons formed and what their origins are. For experimental equipment, we found that two of the instruments used on the Mars 2020 rover could also be used to help us achieve our objectives. So the first is the pixel, which you can see in the bottom left corner. It's able to scan the surface of the moons and identify the surface composition. And the second is RIMFAX, which you can see in the bottom right picture. It uses radar imaging to be able to identify geologic features up to 10 meters below the surface. Next slide.
So our sample retrieval mechanism is going to be a fully autonomous drill that can collect the 50-kilogram samples from each moon. We'll be using the Trident drill developed by Honeybee Robotics since it can meet all our mission requirements. So based on the data that Pixel and RIMFAX will provide, we'll identify various locations that are viable for sample collection. The extracted material is collected via the flutes of the drill, and then it is separated from those flutes using a wire brush. The separated material is then fed into the proper storage container. We estimate it will take about 3.5 hours of drilling on Phobos and about 4.5 hours of drilling on Deimos. On the right-hand side, we can see an isometric view of our drill. And next slide, please.
So for the propulsion system, we broke it down into the propulsion for the service module and the lander. And we conducted a trade study for the propulsion for the service module, selected the Merlin 1D vacuum engine based on its projected cost and its reliability. And this propulsion system is designed to get the service module plus lander from the DST to both of the moons and back. Next slide.
For our lander propulsion selection, we were deciding between an MR107S, which is a monopropellant system, or the R4D system, which is bipropellant. And we decided to go with the R4D due to its extensive use throughout the Apollo missions and its proven reliability and its ability to exceed our desired factor of safety regarding thrust. And although it's more complicated due to the bipropellant system and it adds more weight, we decided to go with the bipropellant system. Next slide.
So the Merlin engine is designed to use rocket propellant 1 as the fuel and liquid oxygen as the oxidizer, which this does create some complications with the liquid oxygen as it's cryogenic. So we need to make sure it's properly insulated, not only for the mission, but for from launch and for the trajectory from Earth to Mars orbit. Next slide.
And for the lander propellant, we decided to go with monomethyl hydrazine as our fuel and the nitrogen tetroxide for our oxidizer due to its better performance versus the unsymmetric dimethyl hydrazine, which is UDMH on the right side. And we chose MMH due to its better performance, its high density, and had to take into consideration its higher freezing point, which requires better thermal control. Next slide. So for our required propellant mass for the lander, we desired a total firing time of approximately 4,000 seconds, and we had a factor of safety of 3, so we allotted for 12,000 seconds of total firing time during the mission. The total propellant mass for the lander was found by multiplying the nominal mass flow rate times the desired firing duration to get a total mass value, along with the mixing ratio given by the manufacturer of the engine. We constructed a system of equations and solved for the mass of the oxidizer and mass of fuel required separately.
Similarly, for the EV thruster sizing, this data was pulled from the SpaceX website for the vacuum engine. Some notable parameters are that the fully expanded nozzle is 2.89 meters and that it has a expansion ratio of 165:1, allowing for enough power to be outputted at any moment in space. Next slide, please.
So for our lander thruster sizing, this is a sketch and drawing by the manufacturer, Aerojet Rocketdyne, and it depicts several sets of dimensions shown in the figure. Each one corresponds to a different expansion ratio and different engines within the same specs. So we're using the middle ratio, which is 164:1. So our nozzle exit diameter is 11 inches and the nozzle length is 19.32 inches. And this engine gives 490 newtons of thrust, and there will be 4 of them on the lander. Next slide.
So for the EV, we'll use 2 separate tanks for our fuel and oxidizer. These two, the liquid oxygen tank will be slightly larger than the RP1 tank, even though we have about twice as much of fuel. This is due because density differences between them. The liquid oxygen tank, as mentioned before, will need a proper insulation to be maintained at its liquid oxygen form at a temperature of negative 163 degrees Celsius. RP1 tank only needs to be maintained below its boiling point, so it's not a cryogenic fuel. And both tanks are made of aluminum lithium alloys, and they're meant to fit within the service module section of our EEV. Next slide. For the propellant feed system, we'll be using a pressurized feed system to keep our oxidizer and fuel tanks pressurized. What this will do, this will control the actual mixture ratio that's being sent to a combustion chamber, so it could be accurate on precise burn and mixture. This system was chosen because it's reliable, and SpaceX also uses this system for its Merlin vacuum engine, which is what we'll be using. The only drawback in this design is that we'll need a 3rd tank of helium, and this will ultimately add a little bit more weight to our design. Next slide.
For the thermal requirement, we broke down the 2 critical environments from LEO to the actual mission environment of Phobos and Deimos. And LEO was calculated using the above formulas, which there's too many terms and equations to include on this slide efficiently. So we included an appendix with the exact values used. And then we estimated to be about negative 53 degrees Celsius, negative 14 degrees Celsius. For Phobos and Deimos, it's negative 112 degrees Celsius to negative 4 degrees Celsius. Next slide. So for thermal control system selection, the main system will be a radiator system with a pumped fluid loop. And we also need enough multi-layer insulation for the crew compartment and the cryogenic fuel container. We also are going to use AZ93 for our thermal control paint. And it's basically using that for the low cost, and it absorbs 13 to 17% of solar radiation coming in. Next slide. And this is an estimation for the sizing of the different components for the thermal control system. The radiator area is estimated to be about 31.8 meters squared for the surface area. That'll likely be broken down into several panels around the EEV. And we estimated the MLI mass to be about 250 kilograms. We'll need about a surface area of 205 meters squared for the white coating. And that brings the total mass estimate to about 947 kilograms. Next slide, please.
So all the subsystems on board the EEV will need power throughout the entire mission, but they can be subdivided into passive systems, which will run constantly, and active systems, which will only be used infrequently. To create a more accurate power estimation, the power consumption here was estimated at a subsystem level, and you can view the power draw of each specific subsystem on this slide. Combining all of these, the total nominal power draw for the EEV is 6.78 kilowatts. Next slide. We then compared power sources to determine which would best suit our mission's requirements. These 3 power sources are commonly used for space missions: radioisotope thermonuclear generators, which I'll call RTGs, hydrogen or alkali fuel cells, and a photovoltaic battery system. RTGs provide consistent and reliable energy, but they produce it at low magnitudes of about 1/10 of a kilowatt, so it might be suitable for some thermal systems, but not the primary source. Hydrogen fuel cells can provide plenty of power, but they're more suitable for short-term missions, and they take up a lot of internal space. Ultimately, we went with a photovoltaic cell with a backup battery system, as they're suitable for long missions, they're scalable and reliable in space. Next slide. So the primary power source for the EEV will be 2 pivoting rollout solar arrays. With the power requirements for the EEV known at 6.78 kilowatts, we can use variables to determine the area. So we considered the power needed, the solar flux on Mars, the solar panel packing efficiency, the packing factor, the angle perpendicular to the sun with the pivoting array, and a correction for solar availability. Ultimately, we determined that the deployed area would be 200 meters squared. And since they are rollout solar arrays, they can be stored in just 16 cubic meters and will have a total mass of 240 kilograms. Next slide. For the power system configuration, from the top down, we'll have the VOSA or rollout solar arrays. They'll generate the energy and they'll be able to pivot to maintain perpendicularity to the sun. Then we'll have the central bus, which will also act as the solar charge controller. This will monitor the power used by all system, and it can route powers as directed by astronauts. Then at the end, we'll have the battery array, which will receive the excess power from the main bus, and it will expend stored energy during periods of low solar availability. The battery array will be lithium ion and have a mass of about 450 kilograms. Overall, this brings the mass of the entire power system to just under 690 kilograms. Next slide. So the power on the EEV needs to be distributed through a central bus so that the voltage and current can be measured at each system in case of any abnormalities. In addition, all the systems need to be able to switch on and off by astronauts in case any abnormalities do appear. So we will use solid state relays to do this, and there will be redundancy since solid state relays are sensitive to radiation. And as far as heat considerations, the panels can also be tilted on command to generate less power and less heat if necessary. Next slide.
So for the structure configuration for our EEV, we've broken it down to the service module and lander. We also have the rover stowed underneath the lander. And at the top of the service module, you can see there's an airlock for the DST and also a connection for the lander. And we did this configuration for a couple of reasons. The main one was to protect the main engine, the main Merlin engine, from possible damage on landing on Phobos and Deimos. And also only using the lander to land on Phobos and Deimos means the total mass required is lower. So the propellant needed for the lander is a lot lower than landing the entire system. We also decided it was easier to deploy the rover from underneath the lander. We got inspiration from SpaceX's Dragon capsule and also the Mars Perseverance lander, where the Sky Crane deployed. It had engines on the side and deployed the rover from underneath. It'd just be easier than trying to lower the rover to the surface. And then also the lander has the 4 engines built in for redundancy. So if 1 or 2 are damaged somehow on landing, we still have enough power to get the crew back to the service module and then back to the DST safely. Next slide, please. The main material we're going to use is an aluminum lithium alloy. We selected alloy AA2090 here, but they're designed to be lighter and slightly stronger than traditional aluminum alloys used in the aerospace industry. For structural supports, we're going to use a titanium alloy, and it has a similar performance to steel, but it's still lighter and less dense. So we thought that would be better to conserve mass. The heat shield, we wanted to use Pika X, and our lander isn't designed, it doesn't have to go through any re-entry, but we do need to protect the bottom surface from engine exhaust from the lander engines. And next slide, please. So for the structural analysis, we did a trade study between the monocoque and the semi-monocoque. And we decided to go with the semi-monocoque because we distribute the loads between the skin and internal support structures, which means that no one piece is failure critical, which this design seems safer for our mission. And the design life is 30 days, but the structure also has to survive launch and being stored inactive in orbit waiting for the DST. And for the analysis, we did analysis of thickness for our internal pressure is 0.3 atm. And we also compared it to pressurizing it to 1 atmosphere. And it shows that pressurizing it to 0.3 atmospheres saves on thickness, it's about 0.28 millimeters, whereas 1 atmosphere is 0.92 millimeters for internal pressure. But the launch environment is the more critical loading environment. We estimate it to be about 0.1 millimeters thickness for the skin, which this is including a factor safety of 2. We also realized that for the semi-monocoque, we'll be able to get these thickness values down by adding the stringers and frame to carry some of the load. Next slide, please.
The EEV telecommunication system is based on utilizing the existing deep space network on Earth, as well as orbiters within the Mars Relay Network in order to transmit and receive data. The deep space network on Earth consists of 3 different communication facilities, one in California, one in Spain, and one in Australia. The DSN supports transmissions from orbiters within the MRN, and updates to the network are expected in the near future, meaning it would be reasonable to assume that the DSN will still be in operation at the time of our mission. The Mars Relay Network is a network of orbiters around Mars that serve as relay transmitters between vehicles within the sphere of Mars and also with mission control back on Earth. Utilizing the MRN allows for higher transmission and reception rates without taking up space on the EEV or the rover. We plan to use either the Mars Reconnaissance Orbiter or the MAVEN Orbiter or similar orbiters in operation at the time of our mission. Since our mission is a crewed mission, a relay redundancy is necessary in order to ensure crew safety, especially in cases of emergency. The primary data exchange method will be between the MRN and the DST. The secondary method will be through any additional orbiters within the MRN, and the tertiary method will use the DST as a relay transmitter. Moving on to the next slide. 3 types of antennas will be used in both the EEV and the rover. An ultra-high frequency antenna will be used to transmit data to the DSN on Earth through orbiters in the MRN. An X-band high-gain antenna will be used to both transmit and receive data directly to and from the DSN. And an X-band low-gain antenna will be used to receive data directly from the DSN. Moving on to the next slide. The 2 orbiters in the MRN that we plan on utilizing, once again, in this mission are the Mars Reconnaissance Orbiter and the MAVEN Orbiter. The Mars Reconnaissance Orbiter is currently in operation and is expected to continue its service through at least the 2020s. This orbiter utilizes both UHF and X-band frequencies to exchange data with the DSN. The MAVEN Orbiter is also currently in operation. However, it is expected to continue its service through at least the 2030s. As it concludes its current mission, it is expected to provide UHF relay for present and future rovers on Mars. This figure illustrates the relay and direct communications between the EEV, the MAVEN Orbiter, and the DSN, which with UHF transmissions used in the relay communications and X-band transmission used in the direct communications.
So we created a CAD model of the EEV in SolidWorks of both the lander and the service module. And we evaluated through SolidWorks the center of gravity and the principal moments of inertia. We also estimated the total mass to be about 79,863 kilograms. And that's including structured cargo and also the propellant. And it's worth noting that the propellant is about 75% of the total estimated mass, which is pretty significant, but it's required due to the large delta V the engine needs to provide for our mission. Next slide, please. So this is just a simplified diagram of our interplanetary trajectory design. You have launch to Leo, then Leo to the Mars 5 Sol parking orbit. And then in red, you see there's simplified trajectory to Deimos, Phobos, and back to the parking orbit where the DST is. Next slide. And for our launch vehicle, we wanted to select a launch vehicle that could go from Earth to Leo and also get from Leo to the Mars parking orbit. And that would cut down size and cost of the EEV drastically if we could find one system to cover both of those trajectories. So the launch to Leo is about 9.4 kilometers a second delta V. Delta V Leo to Mars is about 4.36 kilometers a second. Next slide, please.
Our desired launch date currently is set as November 19th, 2036. And the launch window is the preceding 2 weeks and the following 2 weeks of that date. This launch date minimizes the required delta V to reach Mars at the expense of taking over 2 years to reach the Mars parking orbit. Since the EEV will travel to Mars initially as an unmanned mission, there is no harm in a longer transfer that conserves fuel. Next slide, please.
So we did a trade study. We conducted a trade study to select our launch vehicle. It came down to 4 selections, and we went with SpaceX's Starship due to its projected range and payload capacity. We're able to store the EEV in one configuration in the payload bay. And it's able to take the EEV from Earth to Leo, and then also utilize orbital refueling to then take the full payload from Leo to the Mars orbit. Next slide, please. And this is just a diagram that depicts the EEV loaded into the Starship's cargo area. Next slide, please.
Our overall cost estimation for this mission was determined based on cost of previous missions and cost of existing vehicles of similar sizing and powered systems. Our estimation is grouped into different categories based on major components and subsystems. This includes the launch vehicle, the EEV, which includes the lander and service module, the rover, which includes the rover vehicle and any scientific tools and operations required. And then the final category is telecommunications, which is the EEV telecommunications as well as the rover telecommunications. The overall cost of our mission is $929 million $929,470,000, with the launch vehicle costing approximately $5 million, the EEV costing approximately $675 million, the rover at $232,130,000, and the telecommunications totaling at $17,340,000. So this concludes the presentation portion, and we will now be opening the floor for any questions.
Thank you for the presentation. So any question from our audience? Okay. So if no question from our audience, I'm gonna ask. So one thing is the life support system. Could you please change the slides to the life support system?
Yes.
Thank you.
Slide 13 and 14.
Yeah, I'm just a little curious about this. For the pressure, it's the reduced pressure 0.3. So can anybody give some explanation on this one?
Yeah, I'd love to. Okay, so the reason we went with 0.3 atmospheres instead of a full 1 atmosphere is because if we used a pure oxygen environment at 1 atmosphere, it would be, the fire risk would be pretty extreme. So lowering the pressure to 0.3 atmospheres brings the partial pressure of oxygen close to the partial pressure of Earth's atmosphere, which would give it a similar fire risk of a fire on Earth. And the reason it's, and also it reduces the structural stress on the frame.
So basically, this one means that you have a different oxygen concentration in the atmosphere. Is higher than on Earth? Is that what you mean?
It's just slightly higher. It's 10% higher.
So you mean 10% higher oxygen can make, and this can reduce our atmosphere to 0.3?
No, it's instead of an oxygen nitrogen mixture, it's going to be pure oxygen, but at 0.3 atm. So the partial pressure of oxygen at the oxygen nitrogen is 0.2.
You use pure oxygen in your,
Yes.
okay. So how you think about the fire risk?
The fire risk at 0.3 atm is going to be about the same as it would be on Earth's atmosphere because the partial pressure of oxygen is the same.
Okay.
So it won't burn as fiercely as it would if it was at 1 atm.
Okay, I just remember there's like something like in Apollo 1, that one, because the pure oxygen, it has an accident. So I just want to make sure that if you use pure fuel here, pure oxygen here, that will not cause any potential risk like that.
Yeah, the
Oh.
reason they had an issue with the fire was they did it on the launch pad and they pressurized it to 0.3 atmospheres above at like standard atmosphere. So it was like above 100%
Oh, okay.
pressure. So it was a lot of oxygen in that capsule. This is
Okay.
going to be lowered to 0.3 atmospheres.
Okay.
Yeah.
So as long as your crew can survive on this 0.3 and it does not have high fire risk, I'm fine with it. So another thing is that, so right now I think you have the pressure, the removal carbon dioxide, food, radiation, exercise. Do you have any work done on how to generate oxygen and how do you supply water?
Oxygen is going to be brought along in liquid form. We're going to tap it from the fuel. We're going to bring the liquid oxygen. That's going to be our oxidizer. And we're going to use that as our atmosphere too. And then water, we're going to bring some along with us, but then use a filtration process so we can reuse a lot of it.
Okay, so you have that part of work done, but it's you just didn't put it in the slides.
Yes.
Okay, just make sure that you have that on your final report.
Will do.
And another thing is the structure analysis. Yeah, I realized that you in the slides that you submitted on Monday, there is no 3.1, and this one is recently added. So I was wondering, how did you calculate this 3.1? What kind of analysis you did, and well, in more detail, yes.
Yeah, so essentially, we use that formula, the format from the video you had posted, where we calculated the different compressive loads and different components for launch. So I realized we had calculated that, but I had forgotten to enter it into the CDR.
Oh, okay.
I felt like adding the entire appendix for it would be adding too much to the CDR. So I just decided to add the value, but it'll definitely be the full analysis will be included in the final report.
Okay. So this 3.1 is basically to prevent it buckling during the launch.
Oh yeah, it's the thickness required to prevent buckling during the launch, and that's for the monocoque. But we're going to be reinforcing it, so we're mentioning how reinforcing it with the stringers for the longitudinal, the compressive load can.
Okay, so this 3.1, is it the stringer and the frame thickness, or?
Oh, that was for the monocoque. So that's for the pure monocoque, but since we're going to be reinforcing it, we're going to spread some of the load to the stringers and frame.
So it doesn't mean that you need to recalculate everything.
We were do we need to do that? Recalculate everything?
Because you said 3.1 is based on the monocoque structure. Right? And now you use semi-monocoque. It means that you need to recalculate everything, because the difference of monocoque, semi-monocoque is that monocoque structure, the skin carries all the load. The hoof stress, the longitudinal stress, and the buckling during the launch, everything. And semi-monocoque, you can consider the skin, you can when you do hand calculation, you can just kind of ignore the stress carried by skin. And the stringer and frames become the main load carrying structure. So then if you use semi-monocoque, you need to use, you need to recalculate everything, and sizing basically you need to size the thickness of the stringers and the thickness of the frame.
Okay, I guess I had misunderstood that, so I'll definitely correct that for the final report.
Yeah.
So we were able to just kind of like reinforce the skin, but I see what you mean now. So
yeah, it is reinforced, but it becomes, and then the string and the frame becomes the main load carrying structure.
Okay.
So the whole calculation need to be you need to do it again. And for the thermal control, I guess.
I think that should be up before this slide.
34, page 34 on your original slide is submitted on Canvas. Next one. Yeah, here. So yeah, here. So you have the Q here. Well, I'm happy to see that you have the analysis of the sizing and calculating mass, estimating mass, and the area of radiator, everything. I'm just curious, what value do you use for the Qmax?
For Qmax, at this analysis, we use 8,000 kilowatts for the maximum power output, or the maximum. That's included in the appendix too.
Okay, can I see that one?
Yeah.
Yeah.
Good. Let me see what exact page it is. Yeah, so the maximum electrical power dissipation of 8 kilowatts, and we did the minimum of 6 kilowatts.
So how did you estimate this? Where this 8 kilowatts come from?
That came from the power slide of the maximum. The maximum estimated power was like 6.8, so I added in a little buffer up to 8 kilowatts maximum electrical dissipation. Yeah, that came from the power slides.
So basically, your assumption is that all the electric power energy will convert to thermal load, and that's the only thermal load you consider.
Mm-hmm.
Okay, I think that's okay, but
should we include? Yeah, I'm definitely willing to change stuff for the CDR. So
yeah, so yeah, we know that all the electric power will eventually in the EV will eventually converted to the thermal load. But there may be some other system also will generate the thermal loads, and you want to add in, and then that becomes the total. So you can consider like what other system might also generate the thermal loads in addition to the electric power system.
Like the engines, right?
Yeah, and you can, yeah. So I just want to confirm that this part is like estimated in a reasonable way.
Okay, yeah, no, I understand. I'll definitely include the thermal stuff from other systems like the engine for the final report. And
yeah, I know that the initial power part is the main part, but we may also consider some other system may also generate thermal loads.
Okay, thank you.
Welcome. And just for this presentation, a very trivial thing to mention here, there might be some repetition in the trajectory design. For example, in the first several slides, in the mission overview, that is basically on page 3, I think. This is basically a overview of a trajectory design, and then on the next several page, like 6, 7, 8, I think it basically the same information, just put like in a more separate and in different phase, and the information given in the next several slides, they are the same. Basically, there have the time and duration. So the information is same as here. And then at the very end, I don't know why it shows the trajectory design again. So there might be some repetition in terms of the whole presentation, because we know that we are putting a whole semester's research design in 30 minutes. So we really want to make it like show our key information and make it concise as possible, just in terms of presentation. So it's not a big deal. It's not like just some trivial thing you might want to, like in your future presentation, if you want to do a job interview or anything, try to make it like as concise as possible and don't make any repetition kind of thing, because treasure design, yes, very at the very beginning, and then towards the very end there are several slides about treasure design again. So that is a very trivial thing. So any other question from our audience? So if no other question, then, well, thank you for your presentation. Great job, and work hard on your final report. And remember to send me the video later.
Awesome.
Thank you,
Thank you all for
Professor.
coming.
Thank you.
Thank you.
Have a great one.
Thank you very
Forward,
much.
guys.
Congratulations.
Well done.
Thank you, Dr. Dong, for a great semester.